Hello, hello. Good afternoon, everyone. On behalf of the Scientific Discussion Forum, I warmly welcome you all in today's colloquium. Before we begin, I have a small request to everyone that kindly keep your mobile phones on silent mode and avoid using them during the talk. Every speaker brings valuable ideas and experiences, and by paying full attention, we all have an opportunity to learn something new. So, I request everyone to stay engaged throughout the session. Now, it is my pleasure to introduce today's speaker, Dr. Madhubanti Mukherjee. Dr. Mukherjee completed her BSc in Physics from Midnapur College, Vidyasagar University, followed by an MSc in Physics from St. Xavier's College, University of Kolkata. She obtained her PhD in Computational Material Science from the Material Research Center, Indian Institute of Science, Bangalore. After that, she carried out her postdoctoral research at the Georgia University of Technology, USA and EPFL, Switzerland. She is currently serving as a senior research associate at the Bose National Center for Basic Sciences, Kolkata. We are delighted to have her with us today. Without taking much more time, I invite Dr. Madhubanti Mukherjee to deliver her talk. Please join me in welcoming her with a round of applause. Thank you.
Okay, thank you very much for this opportunity here to present my work and have some discussion on what we did. I hope everyone can hear clearly. Okay, so thank you for the introduction. And when I started my PhD, I started with this energy harvesting materials. I started to read about it, and then I was introduced with the tool. Maybe now every one of you know about density functional theory, and then which basically comes from the quantum mechanics, and then we translate to machine learning nowadays, as you know. So we will touch a bit of everything what I tried to do during my PhD, and we'll see how much we can understand from it. So before going directly to my work, I will just discuss about the research interest or the areas that I have worked from my PhD to postdoc and different positions. So I have mainly worked on different functional materials, which includes thermoelectric materials, some polymer dielectrics, which are energy storage materials, then some materials for application in solar cell devices, then some of the molecules also along with the crystals. I studied for their optical properties and how they can be used for switching performance, and then some materials which can be super hard like diamond. And while focusing on this functional material classes, the governing physics that I was trying to understand was electron transport, phonon transport, that bonding in the crystals, some harmonicity and harmonicity, charge transfer, etc., etc. And then since I work in computational material science, so I have to know about some computational frameworks which can do this density functional theory or molecular dynamics, etc. For those, I have gained experience in different softwares like listed here. If you can see Quantum Espresso, CP2K, etc. And then later on, in the final year of my PhD and my postdoc, I started to learn some machine learning libraries as well, where we generally use Python as a language. So with this, I can kind of summarize my research interest. But today, what I'm going to talk about is this energy harvesting material, which harvest the heat or waste heat to electricity or some kind of useful energy. For me, it's thermoelectric materials, where we are taking some waste heat that we generally get from, let's say, the autos or the buses, or everywhere we are getting this heat that are wasted, and we try to see if we can find a material that can convert this waste heat to some useful electrical energy which we really need. So for that, we will start with some basics of thermoelectrics. So the idea of this talk is basically we will start with the basic physics that we all read everyday life or everyday in class, and then see what kind of fundamental equation that we kind of try to solve, or we want to solve to challenge this materialistic problem, and then to see how we can translate that to a computer, not us, but how the computer solves that for us. So, as you all know, that the thermoelectrics start with this effects called Seebeck effect and Peltier effect. Seebeck effect is when you put a temperature gradient and you get out voltage out of that, and Peltier effect is just the opposite of that. And application wise, we know that Seebeck effect will be useful for a thermoelectric generator, let's say, but Peltier effect is more useful for application like refrigerator, etc. So, since my work is based on thermoelectric generator or materials for thermoelectric generator, I will focus on the Seebeck effect and see how we define different parameters to solve this problem. Now, this figure, if you see, this is basically a thermoelectric generator device where we have hot junction, we have cold junction, we have a temperature gradient from hot to cold side, and then a current or a voltage will be generated due to that, obeying the Seebeck effect principle, and then we will have this current. Now, I think you all have read this Carnot principle, etc., this efficiency. So you can relate to that we will have this heat Q, we will have the work done as W, and then we can define the efficiency as work done by the total heat given. Now, here if you see in the last equation, eta, which is basically the device efficiency, we cannot directly calculate that for a material, right? So for a material is a very, I would say, the other spectrum of a scale, and we start designing the material, and then we go to the device. So first we focus on the material, and for that the parameter that we need to focus on is this ZT. So eta, and in this equation you see ZT, we will focus on that, which takes a form like this. You have S square sigma, S is our Seebeck coefficient, sigma is our electrical conductivity, and your kappa E and kappa L is basically electronic thermal conductivity, lattice thermal conductivity, and T is coming from the equation itself. This looks all simple, but now I will go to the next slide and explain what this ZT means. So when we are talking about this ZT, we say it as figure of merit of a material. That is how good a material is for, or how good a thermoelectric can be for that material. If I choose a material, let's say ABC, how good that can be for thermoelectric application. So we choose this ZT to calculate that or to understand that. So as I say that our AS is the Seebeck coefficient, which is how much voltage is generated when you give a temperature gradient to your system across your material. Now sigma, you all know, is electrical conductivity, and we have electronic thermal conductivity, which is coming from the motion of electrons, and then we have lattice thermal conductivity, which comes from the atomic vibrations. Now, it all looks simple, and we can understand to have a high ZT, we need a large power factor. We say this multiplication of S square sigma as power factor, and we need a small lattice thermal conductivity because we typically don't have much control on the electronic part of thermal conductivity, let's say. But is it very easy to achieve that? Literature says no. Because we see, so in a material, let's say metal, semiconductor, insulator, whatever we take, there is a carrier concentration, that the concept of carrier concentration you all have read. Now, when I see, let's say for a semiconductor or a metal, you see how differently the Seebeck coefficient, which is in the left hand of this y-axis, behave how differently from the other side of the axis, which is electrical conductivity. So essentially, if you see for the metal, let's say, which is that corner metal, you see the Seebeck coefficient is going almost zero when the system is metal. But I have a high electrical conductivity. But with S0, I can never achieve a good ZT, right? So if I now turn to a semiconductor or an insulator, let's say, I have a high Seebeck coefficient, but my conductivity will not be that great. So again, I will face the same problem. So we need to find some sweet spot where probably I will have optimized S or Seebeck coefficient and some electrical conductivity, which can give me a finite, nice power factor and then translate to a good Z. So this goes for the upper part. Now, if I see the same thing for the thermal conductivity, let's say, so for metals, since we have free electrons in metals, we will have very high electronic thermal conductivity. But for an insulator, we will have less electronic thermal conductivity, but there the lattice thermal conductivity can vary from like order of magnitude depending on the system. So I have to be very careful again to choose a material where I can have this balance of electronic and lattice thermal conductivity, and it will be small enough to give me a good ZT. So what happens with all these parameters? They are interdependent, all of this type of thing. What happens when, let's say, I want to choose a material or I want to recommend a new material which could have a very good thermoelectric performance? So I need to know some way out or some intuition. Let's say we will try to develop some intuition to understand what kind of material. Maybe I will look into some of their macroscopical or microscopical properties, and I can understand, okay, this probably will have a thermoelectric performance, nice performance, and then I go to thorough calculation, analytical explanation, everything. Okay. So how do we do that? So first, for that, as I say, what we need to know what makes a good thermoelectric material. We need a high S. But what other things that are dependent or that are influenced to get a high S? So we know this Mott equation, where basically this part, this N and sigma, is coming from the fact that it is del E of log sigma, which is basically how much electrical conductivity is changing when you're changing energy. So we can do some mathematics and we can reach to this equation, let's say. Now, what is this DNDE? That is how many states are available to you for a particular energy range for a unit cell, let's say. We call it density of states, if you have read it. Now, from this equation, we can understand that if my density of states, which is this dN by d for your case from this equation, if it is larger, so basically I have more states available in a particular energy range, then I can expect a very good S or Seebeck coefficient. Instead, if I have a smaller one, small slope or DND, that means less states are available for electrons to occupy, then I will have a less thermal power. Similarly, now I will focus. So this was about the density of states. Now I will focus on electronic band structure. I do not know how many of you have heard or read about electronic band structure yet, but this is essentially the dispersion of energy with respect to your K points, which is basically your reciprocal space, let's say. So in your reciprocal space, how the energy looks like, that is what we try to understand. Now, in this point, let's say I have the first one. So that is the conduction band, the upper one. And the lower one is my valence band. Okay. So electron goes from valence band to conduction band, Now, if I have, let's say, one single pocket, so my electrical conductivity, that is for the electron, very simplified concept, let's say, or very oversimplified, I would say, for one electron that is sitting on that VBM, so there will be only one electron jumping from this to that. So the current that I would expect, or the voltage I would expect for such a single pocket, will always be lesser than the case when I have such multiple pockets, where there are many places where my given an energy or given a perturbation, my electrons can move. So from this, what I can intuitively, understand that if I have a material and I do nothing, I just calculate the energy and in the reciprocal space, that is my band structure, and then I calculate this kind of density of states. From there, I can have some intuition that, okay, this material may be good for thermoelectric material, or maybe I should invest my time into this to understand if this can be, if I can make this better or not. Okay, so these are some intuitive parameters that we would look into in our research. Now, this goes about the AS sigma, this part. And now we come to lattice thermal conductivity. Now, if you remember that plot where AS is going down and sigma is going up, that metal semiconductor plot. So our sweet spot was heavily doped semiconductor, or in a carrier concentration range of 10 to the power 19 to 10 to the power 20 per centimeter cube, right? In that range, we will have our electronic thermal conductivity much lesser. So the only thing that we can tune is our lattice thermal conductivity, which we can define as this, where CV is basically mode dependent or frequency dependent specific heat. Vg squared omega is your group velocity, which is basically in the reciprocal space how much the frequency is changing, d omega by dq. And then we have our tau, which is basically phone-on relaxation time. And I hope that we all know that lattice thermal conductivity, which is basically the ability of a material to carry the heat across the material, it comes from the fact that it carries the vibrational energy. And quanta of vibrational energy is phonon. So that's how we are relating our thermal conductivity to phonon. Okay. Now, and this omega, all omega are basically frequency of the phonon of the material, or the vibrational energy, quanta of vibrational energy, which we are calling as phonon. Now, with this equation, if we focus on, let's say, the first part, which is specific heat, mode specific heat, basically at a particular frequency omega. How do we define that? Your H star omega, which is the energy packet, energy of one packet, right? If I say phonon as a one quanta of vibration, energy of that is H cross omega. D omega is density of states, which is again how much available space is there for the phonon to occupy or to carry the vibrational energy. And then I multiply it by del n0 by del t, which is basically coming from this Bose statistics which phonons follow. And you have some temperature effect, because if you think very fundamentally, as you are all at 0 Kelvin, your material atoms will never move or vibrate or nothing, right? So there will always be a temperature component associated with the phonon, right? It increases the temperature and the vibration start growing, and you will see all kind of features in your phonons or thermal conductivity. But of course, there is a limit. It cannot, the temperature cannot increase indefinitely or something like that. So I get my mode specific heat from that, and I can understand, let's say, looking at this is, let's say, a phonon density of states. Now, if I have some material where I have this kind of localized states, per se. So one state, this localized state is available for phonon, H cross omega energy, at some temperature. So this will give me my mode specific heat, mode like at frequency omega, let's say. And from here, now I can compare, okay, if I have this kind of localized phonon dust, what will happen? If I have something like more broader, what will happen? I can understand all of this from a materials perspective. Now, if we go to Vg, which is our group velocity, defined as del omega by del q, how do we understand intuitively that what kind of group velocity will give me a good kappa or not? From this equation, I can say, okay, this is proportional to group velocity. So if I can somehow reduce the group velocity, my thermal conductivity also will be reduced, which I need for thermoelectrics. But if I look into the phonon dispersion, which is again your frequency of the phonon at the reciprocal space at different Q points, if I look into that, how would I understand? Now, this figure, I hope, I don't know if everyone is if you knows about this figure already, because this figure is directly from detail. Sorry, physics. So this is a phonon dispersion. You have acoustic modes in the low frequency range, and you have optical modes in the high frequency. Now, when I say del omega by del Q, what is that? This is a slope. A slope I am calculating, right? So when I am saying del omega by del Q. Now, from this plot, can you tell me that from, let's say, this mode, what kind of loop velocity or slope I would expect? Or from the upper mode, what kind of loop velocity I would expect? Can you tell me that? Any one of you? Okay, maybe I would just say that. So when I have a straight line and it goes like this, you have a high slope, right? You will get a finite slope. So for this kind of bands, I will have a finite slope where my del omega del Q will not go to zero. But if I have a straight line, do I get a slope there? So if I have a flat band, what does flat band mean? That in all the viewpoints in my reciprocal space, the frequency is not changing much. It is moving with some constant frequency or the variation is not much, right? So in such case, I will get a Vg equal to zero, right? Now, or very less d omega by d. So, what type of bands here I would expect to get a low thermal conductivity? Here, this type of band gives me high Vg because my undefined flow. This type of band gives me low Vg. So, what kind of bands I would prefer to have a low thermal conductivity here from this equation? The upper one, right? You think of. But there is a problem that we can never get only flat phonon modes because we will also have this low frequency phonon modes which can have high vibrational energy in all your reciprocal space than when you are going to this optical phonon branch. So we will have some kind of mixture of this, but we would try to see in this type of like for a material, if I plot the phonon dispersion, I would try to see how flattened my bands are or what type of slope totally I can get, and then I can intuitively understand that okay, maybe this can give me some low thermal conductivity and stuff. So let's go with this. So this goes for group velocity. Now the last part, which is this tau, this is phonon relaxation time or phonon scattering time. So be it electron or phonon or any kind of any statistical particle that we would consider, when they move across your crystal or molecule or anything, they will interact with each other, right? They will scatter from each other. So same happens with phonon, and there are various sources that that kind of contributes to such scattering. Let's say a phonon, a vibrational packet is coming, and I have a defect here. What does defect mean? I have an ordered structure, and I put something very randomly. So it will scatter it will have a extra scattering, right? From the ordered structure, if I compare. So that is, let's say, defect scattering, which is defect is present in all kind of materials when we are growing it experimentally. So you will have some contribution from that. Then it will have boundary scattering contribution. And then you have read about normal and womb clap scattering for phonon itself, depending on if you are scattered within the Brillouin zone or outside the Brillouin zone, etc., etc. So for thermal conductivity, but the main focus for materials design, which I would have, is my phonon dispersion. The first thing I would want to have, I would understand something from there, and then I would calculate more rigorous things, etc., etc. Okay. So we have S, sigma, kappa. We understood what kind of features we are looking into for a materials design. But now the thing is that we cannot calculate it ourselves. Like we can, but for a infinite crystal or system, we can never do it. So we need some help from the computer, and we need to feed these equations to computer. And how do we do that? So there comes this quantum mechanics, which you are reading, and you are very, I don't know, already probably you all have read about it, and you know about this Schrodinger equation. So we focus on this time independent Schrodinger equation at first. Okay. So what we know from Schrodinger equation, that we will have a Hamiltonian for the system, and it will have a wave function for the system defined, right? Now let's say for a system with n small n number of electrons and capital N number of nuclei, we have this Hamiltonian written. Okay, so the first component is your electron kinetic energy. Then okay, don't worry about the notation and everything, it can be very different from what you read in the textbook and stuff. Just focus on the part that we are talking about. So we will have our electron kinetic energy. Then we will have nuclei electron interaction energy, which is the second one. Then we will have electron interaction energy. Then again kinetic energy of the nuclei, and nuclei interaction energy, right? So we have two, let's say nuclei, one element, electron, one element. So for each element we will have kinetic energy and their interaction energy. It's just written there like that for these two. Okay. Now, how this 3n plus 3n? Because for each we have R1, R2, like we have XYZ degree of freedom. So we have 3n plus 3n. Now, even a computer cannot solve it. It will take lots and lots of time. Probably now it will take less time, but yeah, I mean, it's impossible to solve this. So what we need to do, we do some approximation always in physics and get away with which we don't need, to get rid of all those things and stuff. So we just talk about this Born-Oppenheimer approximation, where we are saying nuclei is heavy, the mass is much more than the electron, right? So given a perturbation, the electrons can move really fast as compared to your nuclei, right? So what we are saying, not we, basically Born and Oppenheimer, this approximation, they are saying that given a nuclear coordinate, the electrons can adjust its position instantaneously. So we can get rid, or we can probably not worry about this kinetic energy of nuclei. Let's leave it. And then the last part, which is nuclei interaction energy, that will go like, it will be constant. Okay. So now what we have is just this part, electron wave function. So you see your 3 capital N degree of freedom is already gone, right? You are only given with 3 small n. And then there was some theorem like Weinberg-Cohn theorem. So this is basically an introduction of density functional theory, which is very difficult to do in this short time and in one slide. But yeah, I mean, I had to. So this theorem, after we are left with these 3n coordinates of electrons, this theorem says that all the ground state property will be a functional of their ground state charge density. So we don't think about the wave function or anything else. We will just try to know the charge density of that system, and then we can calculate the energy and other stuff, or the ground state properties, let's say. And this ground state, any system at its minima. So you know, right, that any system that has to be in the down of this parabola. If you see a parabola of energy and coordinates, the system that will be stable will be down position of this equilibrium, like this parabola. So it just essentially says this, that your ground state energy always will be lesser or equal to than that energy function, charge density functional that we are talking about. So now again, it's not ready for computer yet. So then Kohn-Sham came and gave this density functional theory mathematical formulation, how it works, and then we translate it to computer to calculate some things, which we see. So what I was talking about here, you have your properties of system, any system, let's say sodium chloride, which is salt that you intake on a daily basis. So you have your properties of that system, right? Now, if I see from pure quantum mechanics view, These are, let's say, electron within that system, NaCl, let's say. They are all interacting with each other. They have all kind of different interaction. They are feeling their other potential nearest neighbor, etc. It's a very complicated situation happening here. What density functional theory is doing, they are doing this all approximation, energy, charge density functional, etc. And later they are just saying that, okay, I will not worry about this interaction anymore, which is electron interaction. I will just put everything together in some box, let's say, and I will focus on that later. First, let's solve Schrodinger equation for each of this electron, or we would say it Kohn-Sham particle. Okay? So we will have Kohn-Sham single particle equation instead of Schrodinger, which exactly looks like Schrodinger equation, but for each of this electron or Kohn-Sham particle. Okay. So now the problem is a bit solvable for the computer, and this is all this technical thing. Let's not worry about this right now. So we are now ready to put this into computer, and there are some kind of code and mathematical formulation, etc., which is right now in this situation difficult to understand. But finally, what we get with all this equation and lots of physics and one Nobel Prize, what we are left with, this energy and forces that computer gives us when I give them a system, finite crystal structure with a unit cell. With all of this, I'm left with this energy, forces, and stresses. This is exactly what density functional theory gives us without worrying about all those big equations and lots of time, etc. Okay. So this was a long time before. Now things have changed or improved for better. But okay, so these are the output quantities. Now, if you remember the Seebeck coefficient, thermal conductivity, this part, only energy and forces are not enough, right? If I just get energy and force for a particular system, it's not enough to get the Seebeck coefficient or thermal conductivity, or saying, oh, this is a good material for solar cell, or oh, this is a good material for thermoelectrics. We cannot say that. So there are some things that we have to do. We still have to do. It's not done yet. And what are those? So again, we focus on the band structure, which is your K space and the energy in that K space. You vary the Fermi energy to understand. Let's say, if you have a constant Fermi energy, you cannot understand what is going on within the system, right? So how do you take or check the effect of carrier concentration? So there are some approximation again, and you just vary the Fermi energy. When it's, let's say, near the VBM, we would say that it's kind of behaving as p-type, or there are more p-type carriers, right? When it's there in the CBM region, we would say there are more n-type carriers. So you vary them and calculate the S by solving the Boltzmann transport equation, which is basically when we are trying to solve how a set of statistically measured particle move within a non-equilibrium situation with time, right? So that can be collision, there can be diffusion, there can be all sorts of physical phenomena. We try to solve that equation with the energy, forces, etc. that we calculated from DFT. So we mix here the DFT, the Boltzmann transport equation, to get this kind of electronic transport parameter. Okay. So there is the flow chart, basically oversimplified flow chart again. But yeah, I mean, computationally, that is what you do. You take DFT, you calculate, you do all technical stuff, you get the energy, forces, etc. You get the ground state. Then you try to understand what's going on for this material when I solve the Boltzmann transport equation. These things are very fundamental. We all read it in our UG, PG, etc. And now computer is just doing it for us for a larger system. Similarly, for thermal conductivity, if you see, you all know that this equation F equal to minus Kx, right? So when I say crystal lattice, what is that? Your atoms are connected through a spring, basically, spring constant. And then when you give some perturbation, they can vibrate. Your spring's constant is basically changing. If you have a very rigid spring, let's say, it will not move much. And for spring, for our case, it will be chemical bonds. If a system is very tightly bound, when you give perturbation, it does not move much. And the same thing if it is has a weaker bond, let's say, you give perturbation, it moves, you have some good effect in your thermal conductivity. Okay. And then you have this potential energy where you can calculate, you have some different orders within harmonic, with anharmonic. Harmonic is basically when your energy, second order energy, basically del E, del 2E, del X2. And then when you go to the higher order with this equation of your internal energy, then you get different anharmonic contribution. So we try to see how the derivative of energy looks when we displace the atom or give some perturbation. So basically it vibrates, and we try to see if the spring is stiff or it's weak. So basically bonding information, force constant we are saying. And then we solve again some dynamical matrix to get, which is basically your again Newton's second law in a reciprocal space for the phonons, if you see. So all these things we generally read in our textbooks. So here again, I know that it is very difficult to understand what's going on in the computer right away here with these all equations, but at least what I wanted, that what we read daily basis on it in a textbook, at least we can see how computer sees it, or what are exactly important things that we are trying to focus on when we try to get this kind of material properties on a large scale. So we get all these things when we are solving these equations, and then kappa. Okay, so these are the things from textbook. We understand, we give it to computer, because it's not solvable analytically or anything computationally, we do some approximation, and we try to kind of narrow down our search or our space in this way, right? Now, with this, if we have understand this a little bit, not very clearly, let's say, but a little bit, then I would move to, let's say, one of the research project that we actually did with all these things, and try to understand or try to realize if this knowledge can help us to give something new. And that is, the first one is this enhancing our electronic transport properties, let's say. Okay. Electronic transport property means our S sigma, if you remember Seebeck coefficient, electrical conductivity. I want to, very simplified way, if I say I want to find a material which has a good S, good sigma, and good kappa. So it gives me good ZT, and then I get a good paper. That's it, the simplified version. Okay. And how do we go there? Okay. So this is, let's say, for a system, this is your Fermi surface, or if I say very crudely, let's say it's your Brillouin zone, where you have different high symmetry points, and there you have these pockets where electrons can go, because all the energy levels, they have forbidden energy levels, allowed energy levels, right? So this is a different representation of the same thing, let's say. So when we see this, these are the high symmetry points, or those are the high symmetry points from that grand structure, let's say. That sigma, if you see, that is sigma. So those are the high symmetry points where electrons can go. And now, if these points are degenerate energetically, then as we show that we have more power factor, because all the contribution are summing up from the equation, right? So this is what we want to achieve. But this kind of thing we can only see in a high symmetry crystal structure like cubic crystal. Let's say you have a triclinic or monoclinic which has a very low symmetry, then you cannot expect all these sockets to be degenerate, right? Because you have very different kind of symmetry in the system and low symmetry structure. It's not symmetrical to each other. So how do you expect all of this to be degenerate? No, right? So this kind of thing I can only get in a cubic system or a high symmetry system. But then the problem is, because the high symmetry system are very ordered, we will have a very high thermal conductivity, which I cannot, I don't need that. I need a low thermal conductivity. So can I tune a crystal structure, given a crystal structure, can I tune it for a given material that it will have its low symmetry, but it can behave as a pseudo high symmetric system and then can serve my purpose. We will see that. So this is a zinc blend kind of structure. This is a cubic one. If you see the electronic band structure, you see here nice pockets, convergence in the value. So these pockets are energetically degenerate. So I see that, okay, this is a nice system. But then it will have a high thermal conductivity. Now, what we found that there is what we want to find is basically if we can preserve or enhance the electronic properties but lower the thermal conductivity from this structure itself, let's say. So we will focus on just a bit lower symmetry structure, which is tetragonal, which is in symmetry it's lower than the cubic, right? So if you see here, if you see that one and compare this one, it's just penetrating to zinc blend structure, right? And lowering its symmetry here in this structure. But if you compare this, it has a very nice square or cube type framework. Here, if you see in the second figure, it's a bit here and there, not proper square or proper cubic in that the second system. Now, is there a way that I can tune the second system? I can move some atoms, do something, and then if I can reach there, where it still has the tetragonal symmetry, but it has this kind of pseudo-cubic framework as ZNS. Since that is a lower symmetry structure tetragonal, I expect that the thermal conductivity probably will be lower. But if I can retain this pseudo-cubic symmetry, my the electronic transport will be better, right? So I want to achieve this. This is the thing that I want to do. So I have two things that I can tune. One is this eta, which is C by 2A. Don't confuse it with the efficiency eta. So C by 2A is basically your lattice parameter C and lattice parameter A. You are changing the ratio of them. So essentially, probably the volume or some things will change in the system. And then you have this U, which is basically position of one atom. And you can maybe displace an atom and see how they behave. So we start with this many materials, which all are from this tetragonal symmetry, and calculated them and tried to see whether we can reach to this Zn type band structure or Zn type pseudocubic framework. And interestingly, what we see for the magnesium based class, if you see here, so here some things to understand that these bands, when I'm telling this, these are the converge band as we saw in the median of zinc blend structure as well. So we want to achieve this. But since we have so many different structures and they have different eta, so what we are doing, we are replacing this silicon with isoelectronic germanium with tin, and we are seeing this eta is changing. Okay, and the difference between this energy difference between these degenerate bands of, let's say, delta C. So if you see from here and here, these two structures with tin have very less. I mean, the energy are almost degenerate. So we would expect here a good electronic transport properties, right? So is it so? Here we plot this S square sigma, which is your electronic properties, and you see that for the blue one, which is MgSnP2, where here you have delta CF0, that is energies are completely degenerate with tuning this C by 2A ratio of the system. I actually achieve one order high square sigma or large power factor for that system as compared to the other two, just with this isoelectronic substitution. And then we could prove our hypothesis that okay, with the lower symmetry, you can reach the pseudo-cubic framework, and that can affect your electronic transport property. Similar with the conduction band, if you remember the the zinc blend structure, here if you see, we focus on these pockets, right? So for the red one, if I consider those two pockets, it has energy difference of 0.48. But for the silicon, which is the upper one, black, you have only 0.04 EV difference in the energy, and then your pockets are almost converge or degenerate. So we would again expect a high power factor for the silicon one, which we can see in that plot. Forget about the middle one, it's just the energy difference plot. So now we are sure that I can tune my low symmetry structure to pseudo cubic framework or pseudo high symmetry framework, and that can affect the electronic transport. And it does not affect the lattice thermal conductivity at all, because it's only about your electronic band structure. It does not affect the phonon when you change this kind of eta c by 2a ratio. So with this, the summary is basically, I tried to put this hypothesis whether I can tune this structural distortion and lead to a cubic one. That was proved. We can do that, and that multiple degenerate values and valleys and converged band actually improved the electronic transport. And finally, because the lattice thermal conductivity was not really changed. So we got a very nice ZT of 1.67, and our job was done. We could propose a new material which was experimentally synthesized later and then also verified with our performance. And we could able to give a new strategy by understanding what is actually needed to enhance the electronic transport. So I think I would probably stop here. And if you have any questions, you can. Thank you. Now we begin our question clarification. Be able to synthesize the material that we were actually searching for. Yes, we were able to, not us, but the other group was able to. Like what each minimally necessary or what will be the maximum that you can take. Sorry, can you repeat? Like it is taking heat from the surroundings and converting it to electricity. So there will be a threshold that like how much you can maximally take and how much you can take. So that was theoretical to calculate. If you, let's say, I am showing you, let's say, up to 1000 Kelvin. Okay. Now, if I keep calculating and increasing the temperature, I will see that at certain point the curve goes like this, like Gaussian curve. So after certain point, at some maximum temperature, it will start to decrease. Because if you remember, our thermal conductivity and other parameters also have shifts in the behavior. So you cannot like increase the temperature and the negative increase in time. That will not happen. And also, when the experimental group, let's say synthetically, they will have different kind of limitation because we are theoretically, so there are various sources of scattering that is happening inside the body, and how the system is flowing with your setup, experimental setup, that can differ. The environment, everything can differ. So the theoretically which I am getting, we would say that this is the maximum theoretical possible value. It's not the exact. I cannot say that experimentally I will get this value. No, this is the possible. If you know the single crystal purely, you kind of have some control on the scattering and everything, you can reach the possible maximum value, which is we would at least say like that. Yeah, I just have one disclaimer that I did not expect the talk to be this long, so I could not finish the machine learning part that I had, which I actually wanted to talk about. So I would just say 2 lines about the machine learning thing. That when you start right now also the computers are learning from your equation and stuff. What we are saying machine learning is basically the available data space that we have. Machine is now learning that, and so you can use your DFT data or any kind of analytical data, and your machine, you can give some kind of that pattern that you see, or you can also give that to the machine to understand the pattern, and then you can get some results. So this is a very simplified version of machine learning, but I really wanted to talk about that. I could not. So I would say that as DFT, machine learning also is a tool which can accelerate your research but cannot replace your thinking. So that will be the main message that I would like to give.
I want to ask about the quantum particles that we were talking about. You said like it is an assumption that the electrons are non-interactive, that system. But wouldn't that result in a that's an ideal situation?
Yes.
So how is that equivalent?
Yeah, so I will just tell that one thing is that when I'm saying this is non-interactive, we are dealing with non-interactive. So if you remember, for the Hamiltonian, you have your kinetic energy, you have your electrons nuclear energy, you have your electron repulsion energy, right? Now this thing we are saying one external potential, which is electron nuclear. Now this part, this is your doing the approximation on, right? We are saying that this is non-interactive. So with non-interaction, I solve the Hamiltonian with what parameter we have. But now for here, this is a very important part, and you actually have to consider it when you do the real calculation. You cannot remove this part. So you first calculate, you first solve the Hamiltonian without interaction energy. Then you focus on this electron repulsion energy to consider it. But there are two different things. One is one electron is interacting with another. That is one your electron interaction energy. But there is the other thing that one electron is sitting here, all the electrons are interacting. It can achieve some effect, right? Let's say I am here trying to give a talk, and you all are talking about the process. Okay, I will feel the effect, right? So that is my exchange correlation potential. We say in real case exchange potential or exchange potential. So there are two parts of this electron. Now we can calculate this electron because today is electron interaction. I can do it. But this part, what this electron is feeling in here for the surrounding interaction, that is one very important research area in DAP, that is Seebeck, because we are not accurately describe what one particular electron will be. You have many opportunities there. So basically, you feed these parameters later into the calculation, and you kind of go up the ladder towards accuracy of the calculation. That's what.
So you said that isolation substitution leads to band converters, but actually can physical effect that is stress or strain lead to the same effect, or is it negative?
No, stress and strain also can lead to such effects like conversions, because when you are giving strain to a system, your volume or your shape or your parameters are changing. So you take the not similar, I would say, we don't know what kind of effect they are like calculating. But you will see some effects, of course. But the problem is, it's much difficult to give a strain, a structure, make it stable, and all kind of experimentally stability. Then I will just substitute it, because if I can synthesize one element, then I can just do isolatory substitution and synthesize it in the same way. But with strain, it's not very straightforward. That's why you would like to go towards conservation free design certificates.
You spoke about ERG and machine learning, so I can my does ERG consider ground zero state? This is their concept of direction transfer. So how do you expect a machine by feeding a data to bridge the gap between?
Yes, that's what when I was saying that we are seeing very spontaneous, like basically meaning that we are sad that with temperature, with any fluctuation, my convenience of the chemical potential will change in the future, right? But when you are seeing DLT or ground state calculation and zero Kelvin, you cannot just, DLT has this limitation. You cannot put less than 300 Kelvin and do the calculation within only DLT technology. Right? So what we do, we find some way around. For my case, this is you stay under rigid band approximations. You consider with temperature, my band, tectonic bands will not change drastically. So this is true for most of the materials that we work with. And then you change the Fermi energy to understand the chemical potential. And then you feed in the Boltzmann transfer equation and same for the phonon. The phonon is typically temperature dependent fact because if I don't need temperature, how the vibration will come? But here what we do is basically Gaussian approximation or some kind of small calculation where we are confident that if this is my potential energy surface, this pattern it will move only around equilibrium position, but not here. Okay, within this limitation, our DFT works fine. So most of the materials fortunately we can work, but there are systems like the polymers, amorphous material like glasses. This kind of system, it's very difficult to control them with only DFT. So you go to classical molecular dynamics and classical equation of motion to solve them and take the work. So much, then 6 years before the high. So this makes sense. So as I okay, we can so as I say, okay, this is your system right person. And when I am seeing it from the top view, you remember that you had this kind of let's say square. So here I have A, B, C, this kind of material, like the lattice is here and here. Now I am changing what? My C by 2A ratio. Right? C is my Z direction lattice parameter, A is my X direction lattice parameter. Now, if I am changing it in a way that my C by 2A, let's see, C by 2A, where this will be 1, when my C will be 2 of A, right? And wait, if I have a double of A from the C direction, then it's perfect square or perfect this frame one. When I will achieve, when I will have this equal to A and A, then if you from the top you can see that okay, it has a single cubic frame. But let's say I have a C by 2A ratio of 0.3. Right. That means I have a very long C from it and then some kind of A. So now if I see from the top, it will not be like exactly this type of square. Right? When I'm saying about C to A. So basically we need this parameter we found that we are able to achieve this kind of single physics framework when C is big, equal to A. And if it is less than 1 or more than 1, so my this cell volume is changing completely, and that is deviating it from that particular cell to the one.
More questions? So, once again, thank you. And for your time, it's 7 hours.
For a long time.